go. All right? So this type of loop invariant, and tell me when we're done, is we have some numbers, some object to begin with, and we're going to produce smaller inputs. It's kind of like the recursion version, right? I have these big inputs to solve, and instead I make smaller inputs. And if I was doing recursion, then I would get my friend to solve the smaller one, right? And then I would get my answer from my friend's answer. But here, I produce smaller inputs, and I know that my answer will be exactly the same as my friend's answer, right? The answer to the small is the same as the answer to the big. So I just keep iterating, making it smaller and smaller and smaller. And eventually it gets to be so small that I can solve it trivially. And then unlike recursion, where I have to go back and find out what's the answer for the last guy, right? Each of the instances have the same answer, right? So I don't have to go back. I can just return the answer. Right? Everybody got that? Yep. All right, so here's evidently the first algorithm that people claim is an algorithm. It was by Euclid. He was one of those Greeks, right? So whenever the Greeks did their things. And I'm always like, well, didn't the Egyptians build pyramids before that? But anyway, they said, is the first algorithm. So what's the problem? Greatest common divisor. You got two integers, and our goal is to find the biggest integer that can divide into both of them. Right? Greatest common divisor. Everybody got the problem? And how do you do it? Let me tell you how I always did it in high school. Is every number can be uniquely factored, right? 44 is 2 times 2 times 11, right? And the 64 is a whole bunch of 2s. So you set up a Venn diagram where here we got a bunch of 2s, and here we have 11, right? So this is 64, right? You take the intersection of the 2, right? And that's going to be your greatest common divisor, right? But we can't do that because factoring actually turns out to be hard, right? So what are we going to do if we don't know how to factor? Well, what Euclid noticed is that if I get to my two numbers and I replace A by A minus B, right, then the claim is that these two have the same GCD, right? And why is that as a proof? Right? This proof is going to be on the exam, right? If any number divides into A and B, then it divides into A minus B, and it divides into B, right? And if any number divides into A minus B and B, then it divides into A and divides into B. So the greatest common divisors are the same. And of course, I was lying. It won't be on the exam. All right, well, you just say, what is the greatest common divisor of A and B, right? I'm going to claim it's also a divisor of these. Why? Because if it divides into A and it divides into B, then it divides into A minus B. And it clearly divides into B, right? So this guy's greatest common divisor has to be less than or equal to this guy's common divisor, because this one divides into that one. And similarly the other direction. If it divides into A minus B and it divides into B, then it divides into A. Anyway, that's not part of our course, right? All right, let's just use that as a fact. And here's an example, right? Everybody see the example? All right, so what's our algorithm going to be? I've kind of told you already. Our loop invariant is, we started with A and B, but our loop invariant is now now have values x and y, which are smaller because we've made some progress. And our loop invariant is saying that we can even forget what A and B are, and all we have to do is calculate the GCD of x and y and return it because they're the same. Everybody see this as an algorithm? Right? That's the entire algorithm, right? You keep making it smaller until you can answer it yourself, and then you return it. So, right, so again, what are we doing? We're letting these be the values at the top of the loop. We're letting these be the values after we've gone around again, right? And then what's our loop invariant from t tells us that this is true, right? Everybody following? We're just doing the obvious steps, right? The code tells us our new values compared to our old values. Is everybody following this? Because if you're not, you're going to fail, right? This is what you're going to do on the exam. And then, we go forward and not backwards, right? And now we have to prove that the GCD of A and B equals the GCD of our new values, right? We have left side, right side like we did. And how do we do it, right? Well, we use this fact to get to here. And we use this fact to get to here, right? And then we have to prove that this equals this. And how do we do that? We rely on the theorem that we proved before. Right? Everybody see that? And what you're going to get on the test is going to be just like this, right? It's going to be, I know the loop invariant's true for the t values, and the relationship between t plus the new values and the old values, and then I have to prove that it's true for the new values. How do I do it? You say, this has to equal this, and you use your facts to bring them together. Right? Everybody good? And I think we're probably out of time. All right, so what we have to talk about now is kind of running time. Right? So here's an example. We start with those numbers, and remember we subtracted off y from x. And then, we didn't talk about, we don't want to subtract and have a negative number, so we can swap them, right? And then you subtract, and you subtract, and you subtract, and, you swap. Well, you keep going like that, right? Eventually, we get down to one of our numbers is 0, and then anything divides into 0, right? And 4 divides into 4, so the GCD is 4, right? Everybody good? So let's think about the running time. And before we do running time, let's do another example. So everybody feel excited about doing this one, tracing it out as your homework assignment, right? So what happens is you subtract, and you subtract, and you subtract. And how long does this take? Takes a little while, right? Everybody appreciate? Right, so what's the running time? Well, in this case, the value A keeps getting down smaller, so it's order A. Right, everybody? It's a nice, good linear time algorithm. What are we complaining about, right? So let's think about some other algorithms in running time. So here, this is your classic kindergarten algorithm, where you multiply by adding b times, right? So the running time is b, which is linear. That seems great. Here's the high school algorithm, where these could be decimals or they could be digits, bits. It doesn't matter. You take every one here and every one here and multiply them and lay them all out, and you add them up, right? So that becomes n squared. Everybody good? Holler. Really, we're going to do some hard things today. So make sure that you holler if you're not understanding. Okay? So that's order n squared. And now let's take a vote. This is linear time algorithm. This is quadratic time algorithm. How many people think this algorithm is faster? How many people think this algorithm is faster? How many people have no idea? Right? How many people don't know how to put up their hand? All right? So, suppose this was your input, right? And when I was interviewing for IBM, they made me multiply 4-digit numbers together. And I'm like, for IBM? and I got them all wrong, but they said they would hire me anyway. But you can imagine if you really were forced to multiply these, right, could you do it? And which algorithm would you use? I hope everybody would use this algorithm, right? So you have to think of what that means. And then you can say how many minutes is going to take you, how many centuries is it going to take you to do these various algorithms, right? And then here, if we add on an extra digit, how much the time is going to go up, right? Here the time is going to go up from n squared to an additional order n, right? And right, which is not that much extra. And here, the time's going to go up by a factor of 10, right? So that leads me to think that this algorithm is exponential time, all right? So you have to think about why could it be exponential time. Well, let's do another example. I know when you're choosing your password, you think about your girlfriend's name. But if we're doing RSA, then your password is going to be two really big prime numbers that you kind of chose randomly. And then you multiply them together. And what's the time for multiplying, right? If you have 14 digits, then the time is order 14 squared, right? Which is all doable, right? Right? And we make the product public. So everybody knows that if they want to send something to me, they use this product. And my private key is the two primes. And so I can decode it. Not only can I know what your private message to me is, but I can identify myself as being the person who knows how to decode it. Right? So now let's think about our evil guy. He says, all I have to do to steal your money is factor it, right? Because I want to find out what P and Q are. He says, this is not so hard. We just try all the various P's, right? We keep dividing. And the truth is, you only had to go up the square root of n, so it doesn't seem that bad, right? But then you say, well, what's the time? Well, if it's order n, that's linear time, right? But n is the value here, right? It's not the number of digits. And if their number of digits is 28, then the value is 10 to the 28, right? Which is starting to be closer to the number of atoms in the universe, which becomes a little what I would call problematic. Right? Everybody see what I'm saying? Well, for me to count up to this number is about the number of atoms in the universe. Right? This value is big. So if I were to go 1, 2, 3, 4, 5 and count up to that number, the suns would burn out before I got there. So does that make sense? Well, if I wanted to count the digits, 1, 2, 3, 4, 5, it's going to take me no time at all, right? If I could take the digits squared, well, I still can do it in a couple minutes. So, are you following? Everybody, right? All right, so let's think about what running time means. Running time is a function that maps the size of the input to the time, right? And so we have to measure those. And we can measure time in seconds, or we can measure it in the number of lines of code executed, or we could talk about a specific operation like addition, and we count those, which might, and, right? Which of these is valid? Which should we do? Right? Well, it's not that well defined, the second one, because what's a line of code, right? And in some ways, that's the same as this, because a line of code is going to do addition and multiplication and stuff, right? So the point is that all of these times are within a multiplicative constant of each other, right? And we're doing big O. So it doesn't matter. Does that make sense? Now, let's say this was our input. Then our running time, the size of our input could be the area of the paper, right? Or it could be the number of bits to write it down in binary. It could be the number of digits, or it could be the value, right? And which of these is reasonable? All of them. Well, the first one is kind of intuitive. I like to think about it as it's how much time does it take me to give you the input, right? So I can write down the digits, right? I can communicate in some channel using bits, right? So that's the formal definition, is the size is the number of bits, right? Now the number of digits, if you work it out, turns out to be within a factor of 3 of the number of bits. So that's not a big deal. So those are all equivalent, right? But I'm disappointed you all said they're all the same, because I've sort of indicated already that the value is not the same, right? There's an exponential difference between the number of bits and the value, right? So hope you all know that if I take a value, how many bits does it take to represent? It's the log of the value is the number of bits, right? Because if I take the value, then, right, the high order bit here, this is here in decimal, right? It's 10 to the number of decimals. Why? Because this is 1 and this is 10 is the 100, 1,000, 10,000, right? It's going up exponentially, right? Everybody see that? So, right? Right, so there's just a difference there. All right, everybody getting that? And here, let me give you one more example that I've put on many, many tests, and many, many people have gotten wrong. And 20 years ago, Eric Rupin and I argued about this, but I don't know where he stands now. Maybe he's come over to my side. But here's an algorithm, right? So here, let's say we're writing C Java code, and we go loop I equals 1 to n, right? That's my entire program. So what's the running time of this program? How many people say it's linear time? All right, if you think it's linear time, I'm going to give you an input. Here's my input. It takes me, I very quickly can give you the input, right? Now, are you going to run this? Are you going to do this by hand? Or are you even going to run your computer doing this? Right? It's too big. Right? So there's an exponential relationship between how many digits I give you, how many bits. N is a value, right? So I sometimes use capital N to be your value, right? And the size of the number of bits is the log of the value. Right? Does that make sense? Yeah? Everybody good? Yeah? Well, you know what Eric Rupert would say is, well, let's say it's order little, right? He might say that the running time is order n, and no one's going to argue that the running time is order n, right? But if I'm going to ask you the time complexity, right now we're really talking about, now there's no question in this formal sort of words that I'm talking about the formal relationship between the number of bits to write down the input and the running time, right? And the number of bits is log n. So the time is ordered 2 to the n. So if you're going to say the running time is linear, then you have to know linear in what? All right? Maybe I have some extra slides about this in the running time. Maybe I should bring them in here, right? Because, I mean, let's compare it to some other functions. Here, let's say the function being an array x1 up to xn, where each xi is 0 to 9. Right? And then I say, hey, well, let's make n be the sum of over I of xi to 10 to the I. Right? And then I go loop I equals 1 to n. Now, what would you say the running time of this is? Right? The input is clearly of size n, and the running time is clearly exponential. Right? So you're going to clearly say that the running time is exponential. Right? Everybody kind of buy this? Right? Here I'm taking n, and I'm raising it to the power of 10, and then I'm counting up to that. Right? Any arguments about this? Now, what's the difference between these two? Right? There's no difference. Here, I'm telling you what the digits are, and how do I represent n in your computer? Well, the digits are stored somewhere, right? I mean, if this was an array, and I said I'm giving you an array, and the array was of size, had n elements in it, you wouldn't say, hey, I only have one array, so the size of the input is 1. Right? You wouldn't do that. You'd say the size of the input is the number of elements in the array. Right? Certainly wouldn't be how many different values can you put in the array. Anyway, that's where we're at. Right? And so here, what I'm saying is, right, what is the work for me to give you the instance, which is the number of digits, versus the work for you to solve it. Right? And here the value is this big number. Right? So how am I going to do it? I'm going to say, yeah, the running time is order A. Great. But I want to express this as the size of the input. And the size of the input is the number of digits, which is log A. Right? So then the running time is A, which is 2 to the n, or 10 to the n. Right? Are people following this? So this algorithm is not good. In fact, as a general rule, if the input is a value, and what you do every iteration is to subtract by 1, then that's a bad algorithm. Right? What you need to do is you need to be looking at the bits of the value instead, or you need to be taking your value and dividing it by 2. Right? Does that make sense? All right, so that was a bad algorithm, so we're going to try to come up with a new algorithm. And so let's see what the old algorithm was. In fact, we're not going to try to come up with the new algorithm. It's going to be the same algorithm. We're going to just skip steps. Right? We're going to go from here to here to here. Our loop invariants are going to be the same. Right? It's just a matter of how to maintain the loop invariant while making more progress. Right? So here, if we keep, what is our old algorithm? It kept subtracting off y. Right? So let's think. When do we stop? When we stop when you can't subtract, when it's less than y. Right? When you can't subtract again without going negative. So what's the value going to end up here? It's the remainder. People see that? If you take x, you divide by y, right? I is the dividing, and what you get left here is the remainder. Everybody buy that? So, and what is the remainder? The remainder we call x mod y. Everybody know that notation? Right? And now x mod y is less than y, so we might as well swap them if we want the big one first. Right? So here, this is what our new algorithm is going to be. Right? And as I say, it's the same algorithm, just we're jumping over steps. So our new algorithm is given x and y. In one step, we replace them with y and x mod y. Right? Yeah? Oh, because remember before when we were subtracting y, if y became too big, then it became negative when we didn't like that. So we were swapping to put the big one first. And I just know here that x mod y is smaller than y, so I just did the swap. Right? All in one step. So and basically, if the old algorithm did da-da-da-da-da-da-da swap, then we do that in one step. Right? Everybody good? All right, so let's run another example. Oh, here's another problem. Remember, our input now has the first number be smaller, and we needed them swapped, right? So we can think, do we have to write code to swap it? And I like to have as little code as possible, right? So we can think what would happen if we just ran the code, right? What is the code to? Well, what's 44 mod 64? Right? If you take 44 and you divide it by 64, and you take the remainder is 44, right? So this is become 44, and this is y, so it becomes 64. And look at magic. We swap, right? So we didn't need extra code. And so then we take the mod, and we get 20. We take the mod, we take 4. We take the mod, we get 0. And then we know the answer. Right? Everybody follow the new code? Let's do another example. Here are really big numbers. Right? The L to the GCD is 1. Right? You take the mod. Ooh, it came down pretty good. Right? We take the mod. Oh, it came down really good. Really well. Right? You take the mod and we're done. Right? All right, so now we need to think about what our running time is going to be, right? The size of the input is the number of bits to write down A plus the number of bits to write down B, right? And we need a measure of progress. And it could be the X, it could be the Y, it could be the product of the two, right? We could think of different measures. But let's just stick with the value of x. And you'll note here, we went from here to here. The value of x didn't change by very much, right? And so that doesn't seem very good. We need to make progress every iteration, ideally, right? But let's slack the requirement that you make progress every iteration and say, let's say you need to make progress every other iteration. And that's not going to change things by more than a constant in time. So one thing, it's not too hard to prove that in any 2 iterations, if you take any 2 iterations, x comes down by a factor of 2. All right? And the worst case happens to be when this is a Fibonacci and this is a Fibonacci plus 1. Right? Because then the loop invariant is you're going to keep getting Fibonaccis, right? You're going to keep subtracting, and you're going to keep getting Fibonaccis and the next Fibonaccis. But don't worry about that. Everybody kind of good here? Right? So what's our conclusion is that if you go down by a factor of 2 each time, then the running time is going to be the log of the values. Right? And what's good about that is now the running time is big O of the number of bits to write down the number, right? And so this is the time to look at the value, right? If you want to look at the input, it takes you order in time. So you can't expect to do better than that. Everybody good? Now, I'm lying to you a little bit here because each iteration took a log. Each iteration you had to do a mod, right? And really, mod's going to take you order in time, right? Maybe even in log n time. So the running time isn't really n, it's at least n squared. But it's good enough for us. Yeah? Well, if you can prove that every other iteration, if you take the progress here versus the progress 2 following steps, right, that the progress was good, then that's good enough because at worst it's going to double your running time, right? Because instead of it being this many iterations, well, we only counted every other one, right? It's this many pairs of iterations, so the number of iterations is double that. Does that make sense? And sometimes, in fact, our next algorithm, we're going to be doing this same idea of every other step, and it'll be fine. Yeah? All right, well, you need to know, everybody needs to know this if you're in computer science. All right? This is just like that the number of bits or the digits to write down a value is the log. Right? And how can you sort of see that is, well, the value is exponential, right? Oh, I could have used maximum, but, I mean, maximum is the same as big O. Here I'm just saying I have the number of digits in A plus the number of digits in B. Right? The input is A and B, so I had to store A and I had to store B. So the number of digits that I'm storing, the number of bits that I'm storing, is the number of bits to store A plus the number of bits to store B. That's it. Right? Right? Everybody good? All right. There's the algorithm, and we're good. Oh, actually, another cool thing about this algorithm, just so that you know, another whole field of mathematics is if you take the integers mod of prime, then you get a field where you can multiply and divide, and everything is fun. And in order to learn how to divide and take inverses, you use this algorithm.